Welcome and thank you all for joining today's session. We are here to walk through a critical component of modern cloud architecture, an architectural decision guide, choosing your messaging fabric on AKS. As organizations increasingly migrate complex enterprise-grade workloads to Azure Kubernetes Service, one of the most pivotal technical decisions architects must face is how to manage asynchronous communication and event-driven data flows. Over the next few minutes, we will conduct a comparative analysis between self-managed brokers, such as RabbitMQ deployed directly onto your clusters, and managed PaaS offerings, like Azure Service Bus. We will explore the trade-offs between operational control and managed simplicity, focusing on factors like scalability, cost, and maintenance overhead, to help you determine the best path forward for your specific infrastructure requirements. Let's begin. The core decision when choosing a messaging platform on Azure Kubernetes Service centers on balancing operational control against managed simplicity. While AKS simplifies the management of the Kubernetes control plane, teams must still decide who takes ownership of day 2 operations for their messaging workloads. This is a strategic decision regarding operational ownership. On one side of the scale, we have self-managed solutions like NATS and RabbitMQ. These provide full control over configuration, tuning, and topology, but they come with a significant operational weight. Successfully running these requires deep DevOps expertise for monitoring, patching, and disaster recovery. This translates directly to specialized staffing costs and increased organizational risk if internal knowledge is lost. On the other side, a managed platform as a service like Azure Event Hubs shifts the entire operational burden to Microsoft. By abstracting away the brokers, networks, and underlying infrastructure, this approach removes the need for low-level maintenance. Ultimately, choosing a managed service frees your engineering resources to focus on application logic and delivering business value rather than managing infrastructure. This slide profiles 3 distinct messaging archetypes, each catering to different architectural needs. First, NATS with Jetstream is designed for speed and simplicity. It prioritizes low-latency messaging and efficient remote procedure calls, which are essential for seamless microservice intercommunication. While NATS is known for its speed, Jetstream extends its functionality by providing persistence, replayability, and durable streaming capabilities. Second, RabbitMQ represents an archetype optimized for reliable queuing and complex routing. It excels in environments requiring fine-grained control over message flow, achieved through sophisticated exchanges and bindings. Its support for multiple protocols, such as AMQP and MQTT, ensures versatile interoperability across diverse client environments. Lastly, Azure Event Hubs, utilizing a Kafka endpoint, is built for high-throughput, cloud-native ingestion. Its partitioned log architecture is specifically engineered to handle massive volumes of incoming data. Because it offers native Kafka protocol compatibility as a fully managed service, it effectively eliminates the operational burden of self-hosting Kafka clusters while maintaining the same powerful ingestion capabilities. When evaluating the performance of these systems, we see clear differences in how they balance throughput and latency. NATS Jetstream is engineered for speed, focusing on low latency and microservice intercommunication. It delivers a persistent throughput of approximately 1.2 million messages per second, with core NATS reaching up to 8 million for non-persistent data. Its P99 latency is exceptionally low, typically between 0.5 and 2 milliseconds, and it features a built-in RPC pattern for request-response workflows. RabbitMQ, in its durable configuration, prioritizes complex routing and reliable queuing. It offers a persistent throughput of 25,000 to 60,000 messages per second and up to 80,000 for non-persistent messaging. Its P99 latency generally falls within the 5 to 15 millisecond range, and it relies on application-level patterns for request-response communication. Azure Event Hubs is designed for massive, durable data ingestion and high-throughput streaming. It provides high managed capacity with Kafka baselines reaching up to 2 million messages per second for persistent data. Because it is a managed service, latency varies, and it requires an external service to handle request-response patterns. Ultimately, NATS is the clear choice for low-latency microservices. Event Hubs is built for massive data ingestion, and RabbitMQ's trade-offs optimize for transactional reliability over raw throughput. The operational reality of deployment and lifecycle management on AKS can be viewed through three distinct models, ranging from manual configuration to fully managed services. First, let's look at NATS on AKS, which relies on a Helm chart and stateful set. While deployment is streamlined through Helm, the DevOps team remains responsible for the entire lifecycle. This includes managing the stateful set, configuring persistent volumes for Jetstream, and integrating identity controls. As illustrated, you are directly managing the transition from the Helm chart to the individual pods and their associated storage. Moving to a more automated model, RabbitMQ on AKS utilizes the operator pattern. This approach simplifies Day 2 operations by leveraging a Kubernetes operator and custom resource definitions. The operator handles the complexities of clustering, health monitoring, and upgrades, effectively abstracting away the stateful set management. In this flow, the user interacts with the CRD, and the operator manages the resulting stateful set automatically. Lastly, Azure Event Hubs represents a purely administrative approach via the Azure portal or ARM templates. In this scenario, deployment is an administrative task, where users simply define namespaces and topics. Microsoft manages the entire underlying broker topology, storage, and networking, exposing everything through a single endpoint. This shifts the focus entirely from infrastructure management to a managed service model. These three examples demonstrate the spectrum of operational overhead you can expect when deploying messaging solutions on Azure Kubernetes Service. Let's examine the trade-offs between fixed capacity and demand-driven compute models when scaling for efficiency. On the left, we look at managed PaaS scaling, exemplified by services like Azure Event Hubs. This model relies on predictable, pre-purchased capacity. Scaling is typically achieved by allocating throughput units or processing units. While features like auto-inflate allow for some automated scaling up to a defined limit, the graph clearly shows that capacity is provisioned in steps. This often leads to significant idle capacity, where you are paying for resources that exceed your actual demand. The primary benefit here is a very predictable capacity and cost model, but the lack of granularity means you are frequently paying for overhead to handle potential peaks. On the right, we have self-managed scaling for technologies like NATS and RabbitMQ, utilizing KEDA, the Kubernetes event-driven autoscaler. This represents a dynamic event-driven approach, where KEDA scales consumer pods based on real-time external metrics, such as RabbitMQ queue length. As you can see in the graph, the provisioned capacity tracks the demand line almost perfectly. This efficient capacity model offers superior resource efficiency, especially for burstable or unpredictable workloads. However, the trade-off is complexity. This approach requires specialized expertise to configure, tune, and maintain the environment. Ultimately, for organizations running self-managed brokers, KEDA is the essential tool to counter the high total cost of ownership associated with idle, over-provisioned resources. When properly tuned, a KEDA-driven setup can achieve a lower true cost than a PaaS solution that necessitates a 24/7 commitment to a minimum capacity. When securing the messaging fabric, we focus on three critical pillars: client authentication, data in transit, and network isolation. This comparison highlights how NATS, RabbitMQ, and Azure Event Hubs handle these essential security requirements. Starting with client authentication, NATS offers a highly configurable model, including tokens, TLS certificates, and decentralized authentication using N-keys and JWTs. RabbitMQ leverages native TLS with mutual authentication, or MTLS, for peer certificate verification. In the Azure ecosystem, Event Hubs utilizes Azure native identities, such as OAuth 2.0 or shared access signatures. Notably, its Kafka endpoint mandates the use of a managed identity or service principal for robust access control. Moving to data in transit, all three platforms ensure that communication is encrypted via TLS. Specifically for Azure Event Hubs, Kafka clients are required to use SASL SSL to maintain this encrypted state. Regarding network isolation, both NATS and RabbitMQ typically rely on Kubernetes network policies to restrict traffic between pods and brokers. Azure Event Hubs, however, provides a specialized feature called Azure Private Link. As shown in the spotlight diagram, Private Link allows access via a private endpoint within your virtual network, routing all traffic over the secure Microsoft backbone. This effectively eliminates public internet exposure, which is a critical requirement for enterprise compliance and governance, as it completely isolates the messaging fabric from external threats. When implementing mutual TLS on self-managed brokers, we see two distinct approaches for RabbitMQ and NATS. For the RabbitMQ operator, the process is simplified through the use of Kubernetes custom resource definitions and secrets. By defining the secret name in the CRD specification, the operator facilitates seamless certificate rotation. Updating the Kubernetes secret and clearing the SSL cache allows for certificate reloads without requiring a service restart, ensuring continuous operation. In the case of NATS, the implementation involves mounting a config map for TLS configuration and a secret for certificates directly into the NATS pod. A standout feature of this approach is the integration of NATS client identity with Azure Active Directory via Kubernetes workload identity. This architecture links every publish and subscribe action to an auditable, trusted source identity, providing high levels of security and accountability. However, there is a critical caveat to consider regarding the long-term operational impact. While these tools simplify certificate deployment, the management of the underlying public key infrastructure, specifically the issuance, maintenance, and revocation of certificates, remains an ongoing responsibility for the DevOps team. This represents a significant and persistent component of the total cost of ownership that is typically eliminated when utilizing a PaaS model. When evaluating how organizations handle disaster recovery, we compare models based on their operational complexity, ranging from low to high. Starting with low complexity, Azure Event Hubs provides a managed geo-disaster recovery model. This push-button capability is configured at the namespace level, where recovery point objectives and recovery time objectives are determined by the Azure SLA. This approach effectively transfers implementation risk away from the client organization and onto the service provider. At a medium complexity level, NATS Jetstream utilizes Raft Quorum and Valero snapshots. While high availability is achieved via the Raft Quorum, disaster recovery on AKS typically involves integrating Valero. This allows for backing up the entire NATS workload, including the stateful set configuration and its underlying persistent volumes. Lastly, for high-complexity scenarios such as RabbitMQ, we utilize a standby cluster and application-aware backup strategy. Traditional backups are often challenging here because restoration requires an identical node name. Therefore, the preferred strategy is to maintain a separate, dedicated standby cluster. To handle complex stateful dependencies correctly, application-aware tools like Cast and K10 are highly recommended to manage the backup and recovery lifecycle. Defining the backup scope for a Kubernetes workload requires a fundamental shift in perspective compared to traditional server backups. Targeting individual virtual machine nodes is no longer relevant. Instead, we must focus on two critical components: the cluster's declarative state and the application's persistent data. The first pillar is the cluster state. This encompasses the declarative configuration of all Kubernetes objects, including deployments and services, which are stored within etcd. This state is the result of all applied YAML manifests and, in many cases, can be recovered through CI/CD pipelines. The second pillar is application data. This refers to the data managed by your workloads and stored in persistent volumes, or PVs. For specialized systems like messaging platforms, this includes persisted message stores such as Jetstream data or RabbitMQ queues. A successful backup strategy must account for both components to ensure full recovery capabilities. When deconstructing the total cost of ownership, or TCO, we must look beyond just the line items on a cloud bill. True TCO is a combination of infrastructure costs, covering compute, storage, and networking, plus operational staffing costs, which include DevOps overhead, monitoring, patching, and ongoing maintenance. Looking at the self-managed approach on AKS using tools like NATS and RabbitMQ, the cost structure is both variable and complex. Infrastructure costs are primarily driven by virtual machines, persistent storage, and network egress. However, a major hidden driver is idle resources. Over-provisioning to handle traffic spikes often leads to wasted spend unless aggressive tuning with CADA or VPA is implemented. Even more significant are the operational costs. This model requires dedicated, specialized staffing for 24/7 monitoring, debugging, and complex tasks like PKI management. In many cases, these human capital costs actually dwarf the infrastructure expenses. In contrast, a managed PaaS solution like Azure Event Hubs offers a more predictable and abstracted model. Infrastructure is billed based on capacity units, such as throughput or processing units, which inherently includes the cost for underlying infrastructure, maintenance, and automated scaling. This provides a key advantage in predictability for business forecasting. Furthermore, operational costs are dramatically reduced. By shifting the heavy lifting of infrastructure management to Microsoft, engineering teams can reallocate their efforts towards application delivery and innovation rather than system maintenance. Cost optimization for Azure Kubernetes service workloads requires a multifaceted approach, starting with right-sizing your compute resources. It is essential to select VM types that align specifically with your workload needs. Use compute-optimized F-series for CPU-intensive tasks and memory-optimized E-series for memory-heavy applications. Additionally, utilizing a mix of small and large nodes across different node pools allows you to match infrastructure precisely to workload characteristics. Beyond hardware selection, leveraging strategic purchase models offers the potential for significant savings. Spot VMs are ideal for fault-tolerant workloads, such as batch jobs or CI/CD pipelines, providing up to 90% savings. For long-running, predictable workloads, reserved instances can reduce costs by up to 72%. Storage is another critical area for optimization. Avoid defaulting to premium SSDs. Instead, utilize standard SSDs for general-purpose workloads. For unstructured data, such as logs and backups, Azure Blob storage tiers, including Hot, Cool, and Archive, are significantly more cost-effective than managed disks. Finally, implement automated right-sizing. By using the Vertical Pod Autoscaler, or VPA, in recommendation mode, you can analyze historical usage data to fine-tune CPU and memory requests. This proactive approach prevents costly over-provisioning and ensures your environment remains as lean and efficient as possible. To help navigate the selection process, this decision framework aligns specific technologies with your core business requirements and operational capabilities. First, consider NATs with Jetstream on AKS if your primary focus is on low-latency microservice communication, RPC patterns, or resource-constrained edge processing. Choosing this path requires high internal DevOps expertise to manage stateful set operations, Raft consensus, Valero-based disaster recovery, and N-key security. Alternatively, opt for RabbitMQ on AKS when you need transactional queuing, complex routing logic, or support for diverse protocols like AMQP, MQTT, and STOMP. The trade-off here involves integrating Kata for cost-efficient scaling and committing to the management of a dedicated standby cluster for disaster recovery. Finally, Azure Event Hubs with the Kafka surface is the ideal choice for massive data ingestion and a central streaming backbone for long-term analytics and compliance. This option is best suited for organizations prioritizing minimal operational overhead while leveraging Azure Native Identity Management, such as OAuth 2.0 and Managed Identity for their Kafka clients. This architecture presents a hybrid messaging plane designed for maximum resilience and versatility. On the left, we see an AKS cluster utilizing NATs for rapid, ephemeral microservice communication. This localized plane is optimized for fast, low-latency chatter and essential command and control operations within the cluster environment. When internal events need to be escalated or preserved, they pass through a critical event bridge. This bridge connects the localized environment to a durable, geo-redundant streaming backbone, powered by Azure Event Hubs. This secondary plane serves as the foundation for critical business events and advanced analytics. From this backbone, data flows into two primary paths: Azure Stream Analytics for real-time processing and Azure Data Lake Storage for long-term archival and compliance. By leveraging this dual-plane strategy, we achieve a balance between the high-speed, transient nature of NATs and the enterprise-grade durability and reliability required for long-term data integrity and business intelligence. When making your architectural decision, 4 key principles should guide your strategy. First, understand that this choice is a fundamental trade-off between operational control and managed simplicity. Success requires an honest assessment of your team's internal capacity and your organization's risk profile. Second, remember that total cost of ownership involves much more than just infrastructure line items. The cost of maintaining specialized staffing for 24/7 readiness on self-managed systems is a critical and frequently dominant factor in the final tally. Third, for those choosing self-managed systems, aggressive automation with tools such as Kata and VPA is not merely an option, it is mandatory for achieving true cost efficiency and performance at scale. Finally, the complexity of ensuring resilience and disaster recovery increases significantly with a self-managed approach. Utilizing a platform as a service model shifts this substantial implementation risk and operational burden entirely to the cloud provider, allowing your team to focus on core business value.